Okay, good morning all. Yesterday we started our discussion or our review on module 4. So today we will continue with the same. Okay. And yesterday, where did we stop yesterday? Anyone remember? Or what are the topics we covered yesterday? Yes, V antenna. Yes, V antenna. Yes, we have finished V antennas. Just we saw the yes V antenna. Yes, we saw the broad classification of antennas into resonant and non-resonant antenna. Then we discussed V antenna. Okay, so in V antenna, what we saw basically was whether V antenna is a resonant antenna or non-resonant antenna. V antenna, it is a resonant antenna or non-resonant antenna. Can anybody say V antenna is a resonant antenna or non-resonant antenna or any other answer? Okay, what is a resonant antenna basically? Both. Yes. Both. Yes. A V antenna can be set up as a resonant antenna and a non-resonant antenna. Okay. That's the advantage of V antenna. We can construct it as a or design it as a resonant and non-resonant antenna. What's the resonant antenna? A resonant antenna basically there will be a standing wave. Okay, that means it won't be terminated at any resistance. There won't be any resistance at the end. Okay, so there will be a reflected wave. That reflected wave with the ongoing wave both will produce a standing wave within the antenna. Okay, so that is a resonant antenna. A non-resonant antenna, it will be terminated at the characteristic impedance. Okay, so the wave which is coming through the antenna will feel like it is just a the atmosphere is just a continuation because atmosphere is also having the characteristic impedance. So since the antenna has terminated the characteristic impedance, the wave will feel like the atmosphere is just a continuation of the antenna and the wave will travel. Okay, so those antennas are also called traveling wave antennas and resonant antennas in which a standing wave is present, which is called standing wave antennas. Okay, and then we saw the V antenna. These were the topics we discussed yesterday. Okay, so now today we will move on to other classification of antennas. Okay, and in that the main thing is, as you can see, rhombic antenna. Okay, rhombic antenna. Oh, this rhombic antenna has a shape of rhombus. Okay, rhombic antenna has a shape of rhombus, hence the name. What is a rhombus? What is a rhombus? What is a rhombus? Is that just basic elementary things I'm asking? What is a rhombus? What is a parallelogram? What is a rhombus? Okay. What is a rhombus? At least you are having your mobile phones. Just check and at least type the answers if you are listening. Okay, anyway, I don't think I need to explain what is a rhombus in an engineering class. Okay, you are supposed to know this. I'm not feeling like explaining what is a rhombus in an engineering class. That too in sixth semester. Okay, so we will continue. For equal straight side, quadrilateral having same sides. Yeah, somewhat parallelogram with same. Yeah, yes, that's the correct explanation. Okay, at least you come with some sort of answer. So that will be the shape of the antenna. Now I think you might have understood what will be the shape. Okay, the antenna shape will be of a rhombus. At least those who have searched for a rhombus might have understood the structure of the antenna. Okay, antenna has a shape of rhombus. So because of the shape, it is also called a diamond antenna. Okay, the rhombus. The rhombus can be like if the angle between the angle of the corner angles are not 90 degree. If the corner angles are somewhat different from 90 degree, then a rhombus can be thought of as a diamond shape. Okay, so it is also called as a diamond antenna. One end is excited and one end is terminated in an impedance around 800 ohm. So it is traveling wave antenna. Okay. So here is the main difference between V antenna and rhombic antenna. In rhombic antenna, it is a traveling wave antenna or it is a non-resonant antenna. Hence, it is terminated at an impedance around 800 ohm. Okay. So this is a traveling wave antenna. We cannot set up this as a standing wave antenna. Okay, so hence this is traveling wave antenna. What about the radiation pattern? How about the radiation pattern? How it will be? The radiation pattern, how it will be? See, you have to relate all these things. Then it will be very easy to understand. Okay, otherwise you have to just yes, the radiation pattern will be unidirectional. Yes, correct. Like this, you have to study. Okay, you have to relate it with the previous ones. Then the only thing is you just need to remember some sort of differences. The rest will be the same. Okay. So that's how you are going to study this. Otherwise, it will be very difficult to remember each and every point. Okay. So we continue. So it is a traveling wave antenna, and hence the radiation pattern will be unidirectional. The length of leg elevation and height above Earth are chosen to obtain desired radiation. Okay, here the desired radiation is determined by height above the ground, that is H, L, that is the length of leg. That means length of leg means rhombus, it is having a shape of rhombus, so 4 legs will be there, and since it is a rhombus, all legs will be of equal length. And beta is the angle of elevation, and theta is the tilt angle. Okay, so it consists of 4 non-resonant wires of equal length since it is a rhombus. Okay. So four non-resonant wires of equal length will be arranged in the shape of a rhombus. And beta will be the angle of elevation and theta is the tilt angle, and 90 minus beta is equal to theta. That we will see later. Okay. So we are just going to see the image. See, this is the rhombic structure. Okay. You can see here. See here, here the feed is provided or the signal is provided here, and this is the first element. This is the first element, and this is the second element. Both will be having equal length, and this is the third element that is also will be having equal length, and this is the fourth element that is also will be having the equal length. And see how it is terminated. It is terminated at a resistance. Okay. So this H is shown here. H is the height above the earth. Okay. H is the height above earth. And X is the total length of the antenna. Okay. That is not the length of individual elements. The individual element length is L. That is length of each element. Okay. And here one angle will be there. That is the tilt angle. Okay. Beta. And angle of elevation is theta. So here you can see A, here A, C, K, and E. You can see individual radiation patterns of 4 elements. Okay, these 4 elements will be having individual radiation pattern, and the sum of these individual radiation pattern will be the resultant. Okay, in that what we can see? We can see that here the individual radiation patterns were having considerable side lobes. Okay, if you are taking this image, this A, you can see that one major lobe is there, and a considerable side lobe is also there. Okay, here also you can see one major lobe is there, and a very big considerable size side lobe is also there. Likewise here also. But when it is added up, what happened? We can see here one side lobe was there. So, sorry, this can be considered as major lobe. One major lobe was there here, and here also one major lobe was there. These both will get cancelled since both are oriented in opposite directions. Okay, so the resultant will be 0 of these two. But here you see this lobe. This is actually a minor lobe, and here also a minor lobe is there, which is in the same direction. So these both will get added together. Okay. Similarly, here also. See, you can see one lobe in this direction that is considered, that can be considered as a major lobe, and here also one lobe is there, but both are opposite direction, or both are directed in opposite directions. So while we are taking the resultant, or while we are arranging the antennas in this manner, this individual radiation patterns will be added up. So this and this will get cancelled. But what about these two, here and here? They are in the same direction, and thus they will add up. So in short, we can say that this B, C, E, and G, these four will add up together, and this A, D, K, and F, all these lobes will be cancelled. So as a result, we are going to get a very big major lobe in the desired direction of radiation, and some smaller side lobes. Okay, this is the basic idea behind the working of a rhombic antenna. Okay, so that just you can explain it by seeing the picture itself, or if you are just understood the concept, you can draw the picture also. There is nothing much to remember. Okay, one major lobe will be there, and one considerable large side lobe will be there. Likewise, you can draw for radiation patterns and resultant. You can show the addition of all those four. Okay, and since this rhombic antenna has to be terminated at a resistance, it is a traveling wave antenna, or it is a non-resonant antenna. Okay, that's all about the radiation pattern and construction of the antenna. Okay, I think you understood. Then some general points. If angle of elevation is less than 30 degree, it provides greater gain. That is a general characteristic of this antenna. Okay, if the angle of elevation is less than 30 degree, it provides greater gain. That is, that's the normal observation. And the length of leg varies from 2 lambda to 8 lambda. So minimum length of the leg should be 2 lambda, where lambda is the wavelength of operating frequency, and maximum is 8 lambda. Okay. And tilt angle varies between 40 to 75 degree. Tilt angle depends on length of leg. Directivity varies from 20 and 90. So directivity 20 dB to 90 dB maximum. Then the application, point-to-point communication in high frequency band advantage, provides greater directivity than V antenna. Okay, that we can justify from the figure itself. Okay, because the four individual radiation patterns are added up together, and the minor lobes or the other lobes are getting cancelled each other. So we can say that it provides greater directivity. The disadvantage is more space is required for installation. That is the main thing. You have to see. The length of leg already saw that the length of leg varies from 2 lambda to 8 lambda. So if lambda is getting higher and higher means we need a very large space to install this. Okay, so that is not desirable. So it is more space is required for installation, and its efficiency is less. Since the directivity lies between 20 and 90, and we cannot improve the directivity more than that, we can say that the directivity, sorry, the efficiency is less. Okay, so in between, I will just take your attendance. Okay, so we will continue. So the design parameters, we are going to see what are the design parameters. Design parameters we already saw. It is first thing is the height above earth, that is h. Height above, that is h. Then length of leg. All legs will be having equal length, so that is L. Then tilt angle theta. So tilt angle theta will be 90 minus beta. Okay. Now beta is the where beta is the angle of elevation. Okay. So we need to know only theta. From that we can calculate beta. There is no problem. So these only three design parameters are there. In that, two types of design are there. We will see. First one is the maximum output design. You just need to remember these equations. Other than that, there is nothing. This design and all, not at all asked till now in the new universities. Okay, they will just ask the construction and working. That's it. That's all. In that working and all construction, then you can just add these equations. Okay. So maximum output design, that is h. H is the height above the earth. It should be lambda by 4 sine beta, where theta is equal to 90 minus beta. And L is equal to lambda by 2 cos square theta, or theta, if we are substituting by 90 minus beta, we are going to get the second equation. Lambda is equal to cos 90 minus theta is sine theta. So we will be getting the second equation. L is equal to lambda by 2 cos square theta, which is equal to lambda by 2 sine square beta. Just substitute theta is equal to 90 minus beta. This is the design for maximum output. Okay. And second is the alignment design. In that, in this alignment design, h should be lambda by 4 sine beta. There is no difference in h. But only thing is in the design of L, or length of each leg, in the calculation of length of each leg. There, 0.74 lambda is there in place of lambda. 0.74 lambda divided by 2 cos square theta, that is equal to 0.74 lambda divided by 2 sine square theta. Just remember this equation and present it. Other than that, there is nothing. Okay. So we can have two types of design: maximum output design and alignment design. Okay. So maximum output design will give you the maximum output, and alignment design will give you maximum directivity. Okay. So here, these are the some images of rhombic antennas. Figure 1, it is see, you can see that it's a very big antenna. Figure 1, you can see it is a very big antenna. Actually, that's a rhombic antenna used for point-to-point communication in olden days. Okay. So in that you can see that each leg that will be having around 50 to 100 meter separation between them. So 2 lambda was around that much, 100 meter, around 50 meter wavelength waves were used on those days. Okay. So that on those days we had to use this much big rhombic antennas. Okay. So this is a very old image of a rhombic antenna. In that, actually, that was used for point-to-point communication in olden days. Okay. So this is here you can see the major disadvantage of that. The space requirement is more. Okay. And figure 2, in this second figure, you might have seen somewhere at least. Okay, this is now also this is being used for receiving TV signals. Okay. That Yagi Uda antenna and these two. This in olden days, not in olden days, at least some 10 years back, this was very common. And on top of heavy buildings and all, big buildings and all, it was a common installation. Okay. I think some of you might have observed at least because in recent days it is not that much common, but at least up to 10 years back, in 2010, it was a common scene. Okay. So this figure 2, it is a rhombic antenna used for TV signal reception. What is the difference you can observe between these two? What's the difference you can observe? And single loop itself, you can see a particular difference between those two. What's the difference? Whether those two are having same size or which is having smaller size and why? The observation is this only, this is having, one is having a smaller size. Okay. The modern antenna which is used for TV signal reception, that is having a smaller size. Why? Can anybody tell the reason? Okay, after taking attendance, everyone left. What can be the reason of smaller size in TV signal reception antenna which we are using in modern times? What can be the reason? Okay, what quantity? Yes, high frequency. Yeah, correct. See, the higher frequency means smaller wavelength. Okay, the wavelength is the thing which is determining the length of antenna legs. Okay, so in olden days we were not at all able to use the higher frequencies. So we had to keep the length of antenna legs as large as possible. Okay, the 2 lambda to achieve 2 lambda, minimum 2 lambda length, it was very difficult. We have to stretch the length of the antenna to 50 to 100 meters. But modern days, what happened? TV signal and all, we are using high frequency signals. So in order to receive a high frequency signal, a smaller wavelength, that high frequency means smaller wavelength. So 2 lambda is much smaller compared to olden days. So that is the difference. You can see how these things are evolving, how these antennas are evolving over time to time. Okay, so that is the thing here. You can that's the general observation you can make from here. Okay, as engineering students, you have to or you are supposed to have a keen observations. Okay, you should observe what is the difference and analyze and think how or what is the reason for that. Okay. Okay. Anyway, I told you one thing yesterday. Like those who are not written the first series should contact me if they want any marks for that. Okay. So till now nobody contacted me, and I don't know whether they are attending my class or not. Around four people, I think, 4 people were there who are not attended the first series. And if they are not contacting me today, I will treat or I will consider they don't want any marks for their first series, and their first series marks will be 0. Otherwise, I will conduct a retest for them, and they can score marks. Okay. So this is second time I am informing. So today is the last date. If anybody is there who are not returned first series or second series, okay, first series or second series. Somebody might have written first series and they might not have written second series. For them also, those who are not written any one of the series, they can contact me, or those who are not written both the series, they can contact me. Okay, if they want any marks, otherwise that's no problem. If nobody is contacting me today, then I will assume that they are very happy with 0 marks in for the series exams. Okay, so that's it. And if you know or anybody if those who are present here know anybody who are not returned the series exams, you can inform them. Okay. So otherwise, it will be difficult for me. Okay. It is better to avoid 0 marks. So if they are happy, I'm also happy. Okay. Yes, we will move on to our topic. So these are the antennas practically used. Okay, in this figure two, can you are you able to see the resistance, terminate resistance? See this black portion here, that is the resistance. Okay, since this is the field here, we are giving the field, and then the next end we are terminating the antenna at a resistance. Okay, so that's all about the rhombic antennas. Then we will move on to horn antenna. Okay, this horn antenna is a very commonly used, even nowadays also it is very commonly used in aircrafts. Okay, in so many areas we are in our aircraft communication, especially in defense sectors and all. This is being utilized very commonly. Okay, so you might have seen this also. Otherwise, you will see in the next semester. Those who have come to our communication lab, one horn antenna is there. Like we used to sit like in the table where we used to sit. Me and Jimmy sir we used to sit in the table in that, and very on the side of that tables, two large tables are there in which no CRO are there. Okay, there one apparatus was there. In that, two horn antennas were there. Okay, I don't know whether that is present now, or they might have removed that from there. But it was there when while we were doing the labs and all. So it is a very common antenna. Okay. Okay, we will move on to our topic. It's a radiating element which has the shape of a horn. Okay. Horn. What will be horn shape? We will see. It may be considered as opened out waveguide. That's it. Okay. You might have studied about the waveguides. Not you might have. You have studied in that electromagnetic theory. Okay. In electromagnetic theory paper, you have studied about waveguides. So you know what is a waveguide. So it is just nothing but just an opened out waveguide, and a waveguide that is opened out. That is horn antenna. There is nothing much to study. Okay. So a waveguide is capable of radiation into open space provided the same is excited at one end and opened at the other end. See, a waveguide I am placing, and excited at one end means I am just giving signals to that waveguide, and the other end that is just kept open. So what will happen? A wave will guide through the waveguide, and at the open end it will come, and it is capable of radiating outside, or it is capable of radiating the signals to atmosphere or air. But one problem is there that we are going to see in the next point. In a waveguide, a small portion of the incident wave is radiated, and the large portion is reflected back by the open circuit. Okay, that is the main problem here. So we are just taking a waveguide and we are giving signal at one end, and the other end just we are keeping it open. So what will happen? The other end is actually basically the other end is open circuited. So open circuited means there is very large impedance will be there, or the wave will feel like a very large impedance. So very large impedance means what will happen? They will not go, or we will not pass through that impedance. The wave will go, hit there, and reflect back. Some portion will be radiated. Okay, that is the problem with just opening one end. So we should find a way to open the end of waveguide in such a way that it should radiate maximum. Okay, the reflection should not be that much, or the percentage of reflection should be minimized. Okay, normally what will happen if you are just opening a waveguide, just opening a waveguide. Okay, one end you are exciting, another end we are just keeping it open. What will happen? The wave will come and it will feel like at the open circuit end, it will feel like infinite impedance, and the wave will get reflected and will come back, and a very small amount will be radiated. So, in order to avoid that, we have to think of a solution in which the wave will gradually radiate. Okay. So, the open circuit is a discontinuity which matches the waveguide to space very poorly. That's the problem. Open circuit means it is an abrupt discontinuity. So, there is no match or no matching between the waveguide and the space. Waveguide was there, and it at a particular point suddenly it is not there. That is the problem with open circuit. And suddenly at that from that particular point onwards, from waveguide to space, a sudden change. So a sudden variation in the resistance, okay, or impedance. Sudden variation in the impedance. So the wave will reflect. That should be avoided. If we are avoiding that, or an abrupt discontinuity if we are avoiding, we can transmit the wave from waveguide. So the opened out waveguide will transmit the wave into space. That is nothing but a horn antenna. So the problem the problem in front of us is nothing but the sudden discontinuity in the waveguide is causing the wave to reflect. So if we are avoiding the sudden discontinuity, we may be able to transmit the wave into space. Or transmitting the wave into space means that device is antenna. So that is the design of horn antenna, or that's how we are going to implement the horn antenna. Okay, so we will see. And one more problem is there also. Diffractions around the edges will provide poor radiation and non-directive radiation pattern. Okay, just if you are just opening the waveguide means there won't be any particular directivity for that. The waves can go of four edges are there. Okay, waveguide you might have seen. Practical waveguides you might have seen. In that, it is just like a hollow rectangle, Okay, in that four edges will be there. From that four edges, the wave can go anywhere, any side. It is not at all directive. Okay. In order to overcome these difficulties, the mouth of waveguide is opened out, which assumes the shape of horn. Okay. So these are the problems. So in order to overcome these difficulties, what we are doing, in order to provide an abrupt in the place of providing abrupt discontinuity, we are providing gradual discontinuity, a gradual transformation, or we are just opening the mouth of the waveguide gradually into a large one. Okay, so what the wave will feel whenever it comes at the edge is gradually opening up, gradually it is opening up. So the wave will feel that the waveguide is continuing, and at a particular point it can escape to the space. Okay, so that particular shape is having or is set to as horn shape. Okay, that I will show the pictures and all. Next point, abrupt discontinuity is replaced by a gradual transformation. Then all the incident energy will be radiated. Okay, this improves directivity and reduces diffraction. That's the main thing. Directivity, it is improving. Okay, so if a waveguide is there, and if you are able to opening up like this, there is a directivity towards that direction. And if you are opening up like this, there is a directivity towards that direction. So we can incorporate better directivity. Okay. If flaring is done only in one direction, then a sectorial horn is produced. Flaring means opening up. Okay, that opening up is done in only one direction. That is called as a sectorial horn. Now I will show you the basic pictures. Okay. So this is a basic horn antenna. The basic horn antenna. The waveguide you can see. You can see the waveguide here. The wave was coming through the waveguide. Okay, wave was coming through the waveguide, and it opened up gradually. From here, it opened up gradually. Okay, gradual opening is there, and at this point, the wave can escape into the space. Okay, full wave can be radiated. So, if flaring is done in only one direction, then sectorial horn is produced. In the figure we have seen already, flaring is done in all the directions. Okay, the difference I will show you in the next pictures. I will show you. Flaring in the direction of electric field and magnetic field produces sectorial E-plane horn and sectorial H-plane horn respectively. Okay. Basically, we know that electric and magnetic field are perpendicular. Okay. So suppose if electric field is perpendicular to Earth, magnetic field will be perpendicular to that. That means the magnetic field will be parallel to Earth. And if I am flaring up, I am opening up my waveguide in the plane of electric field. Then we can say that that is a sectorial E-plane horn. If I am opening up my waveguide in a plane where H lies or magnetic field lies, I can say that that is a H-plane horn. Okay, so that pictures we will see. If flaring is done along both directions, then pyramidal horn is obtained. That only we saw just now. That's a pyramidal horn. Flaring is done along both the directions, like horizontally and vertically. Okay. Flaring the walls of the circular waveguide, a conical horn is formed. If the waveguide is circular, we will get a conical horn. Okay. The function of electromagnetic horn is to produce a uniform wavefront with a large aperture, and thus directivity is greater. Okay. So electromagnetic horn, what is going to happen basically? The waveguide is opened up gradually, and the wavefront will also will grow uniform manner. Okay, and at the edge, the wavefront will be large. It was small when it was in the waveguide. Then the waveguide opened up gradually, so it will become the wavefront become larger. Okay, that we will see here. You can see various type of horn antennas. Here you can see first one is the sectorial horn flared in H plane. You can see here E and H directions are shown. See, E is perpendicular and H is parallel, okay, to the plane of Earth. So this was the waveguide. This was the waveguide. At this point, the horn antenna we are placing. Okay. And what is the specialty of this horn antenna? It is flaring only in the direction of H, or it is flaring only in parallel direction. Perpendicularly, it is not at all flaring, or it is not at all opening up perpendicularly. Okay, you can see here the width was same, and here also the width is same. But what about in this H plane? In the H plane, here this width was small, and here the width is become very large. Okay, so this is the sectorial H plane horn antenna. Okay, and similarly, you can see sectorial E plane horn antenna. Okay, here E is perpendicular. So what is to be done here? It should be flared in the direction of E. So you can see that the H here, what about the width, what was the width before? The same width is retained, but the height, that means in perpendicular direction it is flared. The height is increased. So we can say that this is a sectorial horn flared in E plane or E plane horn antenna. Okay. And what about the pyramidal horn? You see, this is the most common thing we are using. In the pyramidal horn, in both directions or in both planes, E plane and H plane, flaring has been done. Width is also improved or increased, and height is also increased. So we can see that the resultant is having a shape of a pyramid. So it is called as pyramidal horn. Then this is the circular or conical horn antenna. Okay, conical horn antenna means the waveguide was circular. Here you can see the waveguide is rectangular waveguide. Here on all these cases, waveguide is rectangular waveguide. If the waveguide is rectangular, we can have an H plane horn antenna or sectorial horn flared in H plane, sectorial or the sectorial horn flared in E plane, or flared in both, or it is pyramidal. Okay, pyramidal horn antenna, H plane horn antenna, E plane horn antenna. These three categories are possible if the waveguide is rectangular. But if the waveguide is circular, means it has to be a conical horn antenna. There is no other option, because circle means there is only one quantity, that is radius. So we have to increase the radius only. Here, in case of rectangle, two dimensions were there, length and width. Okay, we were able to increase either length or width or both. But here only one quantity, that is radius. So we have we have to increase the radius itself. So there is a bigger radius here compared to here, and this will be having a shape of a cone. Okay, that you can understand. It will be having a shape of a cone, and hence it is called a conical horn antenna, and it will be producing circularly polarized waves. Okay, so these are the just summary of the points we have discussed so far. Just by seeing these pictures, you can write all these points we have discussed, okay, in the past two slides. Okay, so the things to remember are horn antenna, like it is nothing but a waveguide which is open at one end. Okay, there are some problems in by doing so. We cannot abruptly open waveguide, okay, since it will cause reflection. So we have to gradually flare up the ends so that the wave can gradually escape into space. The flaring can be done either in E plane or in H plane or in both. Hence, H plane horn antenna, E plane horn antenna, and pyramidal horn antenna are there. And if the waveguide is circular, conical horn antennas are used. Okay, these are the basic things we need to remember. Then the design equations. Here one basic horn antenna has been shown. Okay, this is nothing, just to remember this picture, that's all. The horn antenna is flared. From here it is flared, and theta is the angle. Okay, theta is the angle, and L is the total length of the horn. Okay, so this is the wavefront. This dotted lines, these are the wavefront. You can see the wavefront is it is gradually becoming circular wavefront. Since it is opened like this, the wavefront will become circular gradually. Okay, so this delta is the distance between actual wavefront and the edge of the horn. Okay, so the total distance will be L plus delta. Okay, so L, as you can see, it is from the beginning of the waveguide to the end of the wavefront here. Okay, this L will be same up to here since the wavefront is circular. Okay, so some length will be left over here, that is delta. So total length of one leg will be L plus delta. Okay, and H is the total height of the waveguide. So designing equations, just draw this image that you can draw just by understanding the waveguide is becoming circular. That is only that's the only thing you need to know to draw this picture. Okay, so you can take cos theta and tan theta from this. Cos theta is adjacent side by hypotenuse, L by L plus delta, and tan theta is opposite side by adjacent side. Okay, that is h by 2 divided by L. Then theta is you are getting two equations for theta. Then L plus delta, the whole square, that is L plus delta is the hypotenuse. L plus delta or square is L square plus h square by 4. From that you are getting just expands that L square plus 2 L delta plus delta square is equal to L square plus h square by L square, and L square will be getting cancelled, and neglecting delta square, that means we are neglecting the delta square because that will be very small quantity. L is equal to h square by 8 delta. Okay, delta itself is very small, so delta square will be much smaller. That's why we are neglecting delta square. So this is the design criteria. Okay, L we are taking as the length of the leg itself. So h, it is the height or separation between the two legs. L is equal to h square by 8 delta. Delta is the small distance between actual wavefront and the edge of the leg. Okay, so this is the only the design requirements. If flare angle means theta. Here you can see theta. If flare angle is very large, the wavefront on the mouth of horn will be curved rather than plane, resulting increased beam width and reduced directivity. Okay, that we can understand. If flare angle is very big, means very large wavefront will be going to produce. So it will reduce the directivity. Large wavefront means beam width will be increased. Okay. If flare angle is very small, the aperture will be smaller, resulting in reduced directivity. See, if the flare angle is very small, will what happen? It will be very smaller wavefront, and it will also reduce the directivity. Okay. So theta E is 56 lambda by 8 h degree, and theta H is 67 lambda by W. It is just the E plane and H plane half power beam widths. Okay, be half power beam width in E plane and H plane, that is given here. Okay, so the directivity on the general equation is there for directivity 7.5 lambda square by H into W. Okay, and where this that is equal to 7.5 A divided by lambda square. These are just equations. There is no need to design anything. Just remember those equations. Then power gain is 4.5 lambda by H lambda square. Then it is equal to 4.5 A divided by lambda square. Okay. So W is the power. Okay, power radiated. That you will be remember. Then use at microwave frequencies for moderate power gains, measurement of antenna parameters at laboratory. Okay. Measurement of antenna parameters at laboratory. For that only you are using. I think you will be using it in the microwave lab, which you have in the next semester. In S7 you will be having microwave lab, I think. In that you are going to use this measurement of antenna parameters. Okay. In that these horn antennas are only used basically. Okay. So this is the image of the first modern horn antenna. Okay, it is invented in 1938. You can see how big it is. Okay, it is designed in 1938. The inventor is Wilmer L. Barrow, and he is only sitting next to the antenna. Okay, this is the first modern horn antenna. And see, this is a very large horn antenna. This is a 50 feet Homdal horn antenna. It is located at Bell Labs, New Jersey, USA. So two scientists are, you can see two scientists in the pictures, and they discovered cosmic microwave background radiation by using this antenna. They discovered cosmic microwave background radiation in 1964. Okay, so this is established in this antenna established in 1960s. So in 1964, by using this antenna, the scientists were able to find out the cosmic microwave background radiation. So these are the applications of the horn antenna recently. Okay, not recently, but these are the applications. And this is the modern horn antenna we are using in our labs and all. Okay. In our labs, we are using this, and mainly in defense sector, in aircrafts and all, horn antennas are used okay, very commonly. So that's all about the horn antennas. So the basic things we have to remember: without a waveguide, there is no horn antenna. Okay, so there should be a waveguide to have a horn antenna, and horn antenna is nothing but an opened up waveguide. So abrupt opening of the waveguide is not advisable. Or what are the problems that has it is having the problem of diffraction, and in addition to that, it is having the problem of abrupt ending. Since the waveguide is abruptly ending, the wave will feel a larger resistance or larger impedance. Okay, so it will be reflected. In order to avoid that, we are gradually opening it. Okay, that's all. That's all about the theory. Then you have to say about E plane, H plane, and pyramidal, then conical, all these things. Then some design parameters. Okay, that from that a basic question. Okay, L plus delta, where delta is the difference between actual wavefront and the edge of the conical antenna. So edge of the horn antenna, not conical, edge of the horn antenna. Okay. So these are all the things we have to remember in horn antennas. Okay, next we are moving to reflector antennas. Okay, reflector antennas basically they are just reflectors. Okay, you can call it as antennas, but basically they are reflectors. So microwave antenna making use of a reflecting surface. So this is a reflector antenna is nothing but this is microwave antenna making use of a reflecting surface. It is used in radio astronomy, microwave communication, and satellite tracking, etc., etc. Reflector antennas take many geometrical configurations. That is the special thing in with this reflector antennas. It can take many geometrical configurations based on the requirements or based on the reflection. We can say that it can take many geometrical configurations. Most popular shapes are the plane, corner, and curved reflectors. I will show one or two pictures. See, a plane reflector. See, here you see the feed is given in the center. Okay, and a plane reflector is placed, just like a mirror, just like a plane mirror. One reflector is placed here, and here we are giving the feed. The feed is directly incidenting on the reflector, and from that reflector, it is just getting reflected. That's all. That's all about the antenna. Okay, it is nothing but this reflector is not actually radiating. It is just reflecting. The actual radiation is provided by the feed. Okay, where we are providing the signal, and the signal is reflected by the reflectors. This is a plane reflector. Okay, then see a corner reflector. Corner reflector here. See, here the feed is provided here, and since the reflectors are placed like a cone, okay, it is placed at an angle. What will happen? The feed, rays from the feed will incident upon the reflectors, and it will reflect. So we can see in this plane reflector, we cannot say that it is going to a particular direction. Rather, it will be a plane wave. But into the corner reflector, we can say that it is going to a particular direction. Okay, and this corner reflector can be constructed by just by placing two plane reflectors at an angle. Okay, so simplest form uses plane reflector to direct electromagnetic energy in this direction that we see, that we saw already. But it is difficult to collimate the beam in the forward direction. That means it is difficult to have any particular direction, because the plane reflector means they will plainly reflect. That's all. It is. We cannot say that it is going to a particular point. Okay. To better collimate the energy in the forward direction, two plane reflectors are joined together to form a corner reflector. That is only formed here. A corner reflector in which two plane reflectors are joined, and we can say that this is going to a particular point, or we can concentrate this to a particular point. Okay, so that is with the parabolic reflectors. Then reflector antennas. Then next thing we are going to see parabolic reflector antenna. That we will see in the next class. Okay. So this parabolic reflector antennas, all of you have seen. Okay. I think in somebody's home nowadays also it will be there. That is a very common antenna. Okay. Anyway, that we will discuss tomorrow. I think by tomorrow we can wind up the fourth module. The review of fourth module we can wind up by tomorrow. Then next week we will finish off by reviewing fifth module. Okay.